Okay, everybody, welcome back. So we're very pleased to have Barbara Dembin, who will be speaking about coalescence of geodesics and the BKS midpoint problem in FPP. So thank you, Barbara.
So thanks a lot for the invitation, and I'm really sad of not being able to be here in present. So to start this talk, let me introduce you just the model, but of course, I guess you all know the model now, but just to set the notation and to be sure that we are all on the same page. And if there is any question at any moment of my talk, please do not hesitate to stop me and ask the question. So we will be working. So I introduce the model in any dimension d greater or equal than 2, but most of the results in this talk will be mostly in the two-dimensional case. So I will be working on the graph ZD AD, so just the standard graph, and we consider G that is a distribution on R plus. And so we consider the IID family indexed on the edges. So it's an IID family distributed according to G. So this is just the standard first passage percolation model. So on each edge independently, you draw a random variable distributed according to G. And this random variable represents the time you need to cross the edge. And so we can introduce a pseudo metric on the lattice and say that for all xy in ZD, the time between x and y is just the infimum over all path of the time of the path. So it's sum over t in gamma, so over all path gamma that joins x to y. Okay. And so in all this talk, we will be interested in distribution G that are continuous with respect to Lebesgue measure, so that has a density. So G is continuous. And in the case where G is continuous, you know that this infimum is intact, and moreover, it's almost surely unique. So we will say that if gamma is such that txy is equal to the time of gamma, then we will say that gamma is the geodesic between x and y. And here, really, when G is continuous, the geodesic is unique. So gamma is the geodesic between. And so we will often use the following notation. We will denote gamma xy to be the geodesic between x and y. And let me just now introduce you another thing that I also guess you all know, but just that will be an important tool for our result. So it's about the limit shape. So if I fix some time t greater or equal than 0, and I look at all the points, so if I start an infection at 0 and the infection propagates through vertices, and the time the infection propagates from one neighbor to another neighbor is given by the time along the edge. So if I propagate an infection like that, and I look at BT, that are the sets of infected vertices at time t. So these are the sets of points in the lattice such that the time between 0 and x is smaller than t. And so this set is a random set, but if you wait for a long enough time, this set will look like a deterministic set. So there exists a deterministic set that we will denote BG, such that if we look at bt over t, it in some sense, when t is large, it looks like the limit shape bg. So this was first proved by Cox and Duret. And so this is really the limit shape. So it says that if you wait long enough, the shape it will look like is no longer random at first order, but it really looks like something deterministic. And so in the assumption of our result, we will really use things about this limit shape, because if you know things about the limit shape, you can deduce information about the geometry of the geodesics. So for us, it will be so we will have an assumption on this limit shape that will induce some properties on the geometry of the geodesic. So now what are we interested in? So we are interested in the coalescence of geodesics. So what's coalescence? So the idea is that I look at a set of two endpoints. So, and the starting points are these ones, and the ending points are these ones. And you see here that the starting points and the endpoints are very close to each other compared to the overall distance they have to travel. And so what we hope to see is that, like the geodesic, they will just like coalesce and then split like that. So they will. So the coalescence means that they have a lot of portions in common. And so what's the idea you can have in mind is that there is somewhere in the lattice a kind of highway. So this is like this is a kind of highway where you go very, very fast. And typically the optimal thing for the geodesic is to just take the small roads to join the highway and then like travel together along the highway, and then at some point split again with the small roads to join their destination. So it seems natural to believe that if you look at two geodesics with really close endpoints, they have to travel together along the way. And this problem of coalescence, we will see, so I will explain later how this problem of coalescence is related to another problem. So it's the problem, it's what I call what is called the BKS midpoint problem. So it's Benjamin Nicolai and Schramm. So in a paper in 2003, they were studying fluctuations, upper bound on the variance or on the time, so fluctuations in first passage percolation, and they needed to understand what's the influence of an edge. And the influence of an edge is roughly, is this edge is important or not for the overall time. And the fact that is important is roughly equivalent to the probability that the geodesic goes through that edge. And they were not able to prove that if you pick one edge in the bulk, the probability that a geodesic goes to that edge is really small. And so they raised the following question: is what's the probability that 0 belongs to this? So you have 0 here minus NE1, NE1, and you wonder what's the probability that the geodesic goes to 0. This is why it's called the midpoint problem, because it's in the middle of the geodesic. We wonder how likely it is that the geodesic goes exactly to the midpoint. So of course, it's natural to expect that this probability goes to 0, because we expect that the geodesic has a lot of fluctuations, vertical fluctuations. So for instance, if you look at the straight line, so we expect, like in dimension 2, we expect that the vertical fluctuation, that is the amount of space it deviates from the vertical line, we expect this vertical fluctuation to be of the order n to the 2 third in dimension 2. So we expect that the geodesic, the maximal height it can reach is of order n to the 2 third. So if you believe that, like the geodesic, if you look at the middle, if you believe that all the points here are almost equally likely, you you will guess that this probability in dimension 2 should behave like n minus 2/3. So you expect this probability to, so this is of course a lot of very conjectural, but it's proved in case of a solvable model in, for instance, in last stage percolation, in some cases that are solvable, these kind of things are proved. So we expect that this probability to be really small and to be like polynomially small. And so this question was left open until like 17. So there was 2 results. There was Dembin and Hanson. And then in 19, there was Albert and Hoffman. And so what they proved that this probability goes to 0, but without quantitative control on how fast it goes to 0. And so here they had the assumption on the limit shape, like differentiability on the boundary of the limit shape. And here they have no assumption. So to study that, they study the coalescence of infinite geodesics through Gaussian functions. And so they were able to prove that this goes to 0 because it's a bit linked to the existence of B geodesics, but there was no quantitative control on how fast it goes to 0. And let me just mention another result, but that is a bit of a different flavor. That's the result of Alexander in 20. And here he was able to obtain like quantitative things on that, but with very strong assumption on assuming that all the quantity, like the variance and the vertical fluctuations, behave like polynomials. So that's really a strong assumption that up to now were not verified for no distribution in the context of a specific population. But so until now, like this result was only proved to go to 0, but without quantitative a quantitative speed. So these are the 2 problems we are interested in. And so if you have any question, that's a good moment to ask. So if everything is clear, I can now present the results. And here again, it's in dimension 2. And these 2 results here were also in dimension 2. So here we are in dimension 2. So let me first state the result about coalescence of geodesics. So we make some assumption on the distribution. So we suppose that G is continuous. So it has a density, an exponential moment. But these are more like technical assumptions. And we made also an assumption on the limit shape. So we made the assumption that the number of sides the limit shape has is at least 40. So what does it mean, the number of sides? So if the limit shape is a polygon, then the number of sides is just the number of sides of the polygon. And in the case the limit shape is not a polygon, then the number of sides is infinite. And so this is an assumption of the limit shape, but it's an assumption that is weaker than assuming, for instance, differentiability of the boundary. And in fact, this assumption, we were able to verify that it holds for a special family of distribution. So this assumption is quite built in some sense. So these are our assumptions. And so now I'm going to state a formula that may look ugly at first, so don't be scared, I will explain on a picture. So since it's a quantified result, there will be a lot of epsilon and deltas. But I will explain. So, okay, so this formula may look ugly at first, but I'll explain in a picture. So what? So first, there are two parameters. So epsilon quantify how close the endpoints are, and here you see like the larger epsilon is, the closer the endpoints are, and so the better your control is, because the closer it is, the easier it is to control. And your delta here, it controls the delta here is the symmetric difference. So it controls like what's the amount of portion they don't have in common, the geodesics. So we have like 0 here, y here. This is a box of psi y, and same here. And so what we say is that with high probability, so probability that is a polynomially good, so with a high probability, we have that if you look at these two cubes, you have in the same time that all the geodesics, you take any two endpoints in the cube, and you know that on this good event that happens with a very large probability, like you look at the geodesic, they will really coalesce along most of the way. That means that this portion here, where they are different, is going, this is what is the y1 minus zeta. So it's really, the portion where they are different is really negligible compared, because we know this is really negligible compared to the distance between their endpoints. So it's really, they're really fast, they join really fast along this highway, and they split only at the end. So this is what this theorem says. It says that you have a good probability that all the geodesics starting here and ending here coalesce really quickly. So this is our first theorem. And now thanks to this theorem, we can deduce, and I will explain how we can deduce a result about the BKS midpoint problem. So, yeah, so it's about controlling inference of edges. So under the same assumptions, you have that there exists C such that for all y in ZD, so the probability that Z is in the geodesic from 0 to y, it decays polynomially fast. So you still have this log. And this quantity is the distance from Z to the endpoints. So what does it, why do we have that? It's natural that like you have 0 y. Of course, if Z is, we don't make any assumption on Z. Z does not have to be in the bulk. So of course, if Z is really close to one of the endpoints, you don't expect that the probability that the geodesic goes to that point is really small, because it's the closer it is from the endpoint, the larger the probability is. So this is why you have this to account that. And if you are in the bulk, here what you have here instead of this is y and 1 to the power 1 over 16. Okay, so you really have a polynomial decay of the probability that Z is in the geodesic. And this is not only for the midpoint, but really for any point. Okay. So yeah, so what this theorem says is that the probability that you go through a given point decays polynomially fast if this point with the distance if this point is in the bulk. So now let me so again, if you have any question, please feel free to ask. Okay, so now I'm going to go to the proofs. So, so what I want to prove is the second theorem, and assuming that the theorem with using the theorem one. So we will see how the fact that we know things about the coalescence help us to deduce something about the midpoint problem, about the influence of edges. So proof of theorem 1 implies theorem 2. Okay. So for simplicity, to not make our life too complicated, we will assume that Z is in the bulk. That is, it's not close to the endpoints. So we have 0, Y, and Z. And so we set L to be Y 1/8 minus epsilon, with some epsilon that we will choose later, because we will have a small optimization. And so what we want to control this probability. And here we are going to use an averaging trick. So the averaging trick was first introduced in a different form than what I will present here, but in the paper of BKS, Benjamin, Kala, and Schramm. And here I will use a kind of averaging trick that is more similar to the one that was used in the paper of Dembin, Hanson, and so where they prove the lower bound on the variance, but for more general distribution, extending the work of Benjamin, Kala, and Schramm. So we are going to use an averaging trick, and so you will see what is an averaging trick. So the first step, so when you have this, so and lambda L here is going to be the box minus. So the first step is to use translation invariance. So this is the same of summing over W in lambda L, probability that Z plus W is in gamma W V plus W. So here I did really nothing. I just used the translation invariance. Any of this probability is equal to this just by translation invariance of the model. And here L square is really the size of lambda L up to some constant. Yeah. And so now what I want to do is I can upper bound this by this sum. So the union over U of gamma U V plus U with U in lambda. So here I make the probability bigger because here it's a larger set than here. And on this I can rewrite as expectation of the sum of W in lambda L, indicator of Z plus W in this union. And here I only, sorry, it's not, it's a Y. And here I only use the fact that you can write the probability expectation of an indicator, and that you have a linearity. And not this, we can say that it's smaller than the expected intersection of the box Z plus lambda L. In fact, it's equal with this union. So we have changed like things that was related to the fact that one point is in on geodesic, that to another thing that is a set of geodesic, the intersection of a set of geodesic with one box. And we will see that this is much more easy to deal with. So we have the picture here. So here I put all the boxes, the corresponding boxes. And recall that thanks to Theorem 1, with really high probability, we can assume that all the geodesic that starts here and that end here, we can assume that they coalesce, that they coalesce really quickly, such that if there is one that goes through the box here, or everyone, when it will go through the box, it will go through the box by going through the same geodesic. So in fact, all this union that can be really huge, inside the box, it's only one geodesic on the good event that they all coalesce. And so, yeah, all the geodesic here, they all form only one path when they intersect to the box. And so that means that on the good event where they coalesce, you just have to compute the expected intersection with a geodesic within a box. But this is something that is really standard in space percolation, and it's easy to compute. So it will be the expected intersection with a geodesic with a box will be just of the order of the side length of the box. So now so my computation, I can split it in two. So I have CL, so it's the part where you have coalescence, and you have plus expectation of this indicator that you don't have coalescence, no coalescence. And when you don't have coalescence, you cannot say much about this intersection. But you can do the most naive bound you can is to say that this intersection is smaller than the total size of the box. So you can just say that this is just smaller than L squared. So you will have CL plus L squared, and expectation of the indicator that there is no coalescence is the probability of no coalescence. So it's, if we go back here, so here our delta here is equal to 0, because we don't care to have a very good control of the coalescence. We just need to be sure, since it is in the bulk, we just need to be sure that it coalesces like for like a 99% of the path will be enough. And this corresponds actually to a delta equal 0. So if we forget about the log term, we just have y epsilon here. And I recall that this was L squared. So now if I divide everything by L squared and I replace L squared by its value, I have the following. So it's smaller by 1 over, so L was y epsilon constant. And here you see that the right, you have a very small optimization, and the right choice to make is to choose epsilon equal 1 over 16. And of course, here I forgot about all the log terms to be more simple. So here what we have is that if we know coalescence with endpoints on a cube, inside a cube, then we can, using the averaging trick, we can deduce things about the probability that one point is inside a geodesic. So this concludes the proof of theorem 2, assuming theorem 1. So if there is any question on the proof, okay. So if there are no more questions, I'll now explain the main ideas of the proof of theorem 1. So let me recall that the proof of theorem 1 is that we want to prove that, like, with a very high probability, all geodesics starting from here to here, we want to prove that they all coalesce, and with a really small symmetric difference. So to prove this theorem, we have a key proposition, and in fact, this key proposition, it also holds for any dimension, not only in the dimension 2. So so I'm going to be really vague on the terms in the proposition because it's a bit heavy to introduce precise definition. So the propositions say that with a high probability, a geodesic has a lot of attractive intervals. So I will explain roughly what does it mean to have to be an attractive interval. So we have our geodesic like that. And so we are going to have like two. So let's say this is of order n, the total length, and we will have like two parameters, m and r, and they will both be some small power of n. So it's quantified, but we won't pay too much attention on what's the value of alpha and beta. So m is going to be the typical size of interval. So we just split like that the geodesic into interval of size m, and r, and we are interested in like tubes along the geodesic of size r. So what does it mean? What is the definition of an attractive interval? So an attractive interval is an interval such that if you have a geodesic that stays along this tube the most of the time along the tube like that, then in fact this is not possible that this geodesic does not intersect it, because so in attractive interval, like the time along the geodesic is so interesting, is so low that any path that come close to it, it just want to go and follow this path, because the amount of the price, the cost it has to pay to just make the connection like that is over the r, and this cost is really compensated by the gain it has to just join the geodesic. So that means that on attractive interval, if you know that you have another geodesic that is close on this interval, that means that they intersect on this interval, because a geodesic cannot, along attractive interval, a geodesic cannot stay really close and not intersect, because just the geodesic, the right geodesic is so interesting that another geodesic that come close just want to connect and then travel along it. So roughly this is what's an attractive interval. Another way to phrase that is that the geodesic is a highway locally. The meaning all the other possible paths around the geodesic are much worse, that when you want to travel along here in the neighborhood of here, you just want always to take the highway. Like the small roads are not efficient enough. And so we have a proposition that says that a geodesic has a lot of, there are many attractive intervals. And so how do you prove such a thing? And we will see how it is useful after that. And as I said, this proposition is true in any dimension. So if you want to prove that the geodesic has a lot of intervals, and there is basically two things you need to do. You first need to be sure that like along the geodesic, there are a lot of for a lot of intervals along the geodesic, it's fast enough. And fast enough means that the time like along the orange thing is better than what you would do in expectation to go from there to there. You have to be sure that there are a lot of portions like that. But if I know that the time to go from here to here is better than the expectation, then maybe it's a highway, but maybe there are other highways around. So it's not enough to be sure that this is fast, faster compared to the expectation to go from there to there. You also have to be sure that around you there are not other highways. And so you have to be sure that the environment around you is bad enough such that the orange thing is really the local highway, and that so that any path entering this tube just wants to go along the highway. So there are really two things to do to prove that there are a lot of portions of the path that are interesting, plus a lot of intervals where the portion of the path are interesting, and the environment is also bad. You have to have simultaneously these two properties. So this is the rough idea. And now, so let me give you a bit more detail. So first, to prove that along the geodesics, the time is, there are a lot of intervals where the time along the geodesic is interesting. And interesting for us means like better than what you would do on expectation. Better than the expectation from here. So to prove that, you use Talagran concentration inequality in both in the global scale and in the local scale. And just the Talagran concentration inequality says that it gives a control that it says roughly that the time between 0 and x minus the expectation between 0 and x, this is smaller than, let's say, log x. This is to have it with a high probability square root of size of x. So, and with high probability when x is large. So this Talagran concentration inequality says that roughly gives a control on the concentration. It says that the difference between the time and the expectation is at most square root. So, well, to prove this, so I won't do the detail because it's a computation that I don't want to do here. But you use Talagran inequality in two ways. You have the global way, so you know that the time from here to here compared to the expectation is at most like square root n. But you know also that locally the time between here and here, the difference between the time and here and the expectation is at most square root n. And so this means that you know that you have a global control on the thing, and you know that you have the local control. And so you know that the worst case that can happen to you cannot happen. And the worst case will be that you have some paths that are very, very, very interesting, but so you only have a few of them. And that's not what we want. But since you have the control of square root m, you know that the interesting path, they cannot be more interesting than square root m lower than the expectation. And since you know that the total difference has to be over the square root n, you can find like a lot of paths that are interesting. So it can be a bit higher than the expectation, but it has to stay close to the expectation. And so by doing that, you can prove that you have a lot of paths that are interesting. So it's just a computation using these two kind of concentration both at the local scale with the small interval and at the global scale. And not, as I said, it was not sufficient to know that this is good. You also have to know that the environment is bad. And to be sure, to ensure that the probability that the environment is bad, knowing the geodesic here, so to make the environment bad, above the in the tube outside the geodesic, in the tube bad, we use a Mermin-Wagner type argument. And so what's a Mermin-Wagner argument? So it says that so in the tube, you have a collection of times in the tube. And roughly what a Mermin-Wagner type argument says is that you can modify just a little bit all of the time, and it will not change the probability by too much. So, and there is a way to do that such that it does not change by too much, and it's related to the number of edges in the tube. So in fact, if you do this transformation, the square root of the size of the tube, what it says is that you can really change all the time in the tube, like make the environment worse by increasing all the time by just a little bit. And this just a little bit is exactly such that you don't see the difference in probability. That is, if I give you this t or this t, you cannot be able to say, oh, I've made a change on this t. You don't see the difference if you add all the, if you make a really small increase on all the TE, you cannot see the difference. Like if I give you this realization, you are not able to say if I've added something or not. So it's really a small increase that you don't see that much the difference in probability. And thanks to this really small increase, you can make sure that the environment above is bad. And so you can make sure that you have a lot, that if you know that this is good, you can make sure that the environment above is worse. So thanks to this tool, you can make sure that you can really build a highway so that you really have an attractive interval, that you can really build an attractive interval. And so for that, we also use the fact that if you condition on the geodesic, on gamma equal P, then all the weights outside P, they stochastically dominate IIG. And this is just by FKG. Just the fact, like the worse, the higher the time outside the PR, the better, the easier it is for gamma to be equal to P. So you use here FKG and kind of stochastic domination on the times. Okay. But really, this proposition really is to say that yeah, you can ensure that a geodesic has a lot of attractive intervals. So if you have any question on this proposition, so here, yeah, I did not enter too much detail. I really stayed really high level to just give you intuition on what's going on and have the main idea of it. So if there are no, sorry.
Yeah, we do have a question.
Great.
Hi, when you are using these inequalities to get bound on the probability of these interesting or attractive paths, are you just wanting to say that they happen a linear proportion of the time, or do you need some stronger bound than that that you are able to get out of these inequalities to
on the probability or on the time?
The probability, say, of a given tube having an interesting path.
So actually we prove that the probability that an attractive interval is really small, but it's okay for us because it's really small, but since you have a lot of intervals, at the end you will have a lot of them. Even like we don't prove that every interval has a good probability to be attractive. It has only a really small probability of being attractive, but it will be enough for us.
Okay, thank you.
So I think I had, sorry, my thing crashed, but no problem. Okay, can you see it again? It's okay. Because it crashed at some point.
Yeah, we can see it just fine.
Okay, so know how to use how to use this proposition to prove what we want. So, and what we want is like theorem 1, like to prove that we have coalescence. So again, I will remain really sketchy. So we have like 2 cubes like that. And we want to be sure that they all coalesce. So what we do is that we are going to trap this cube by geodesics. So I look at the geodesic like that. So the first one is the translate of the second one. And if I manage to prove that this geodesic coalesce, so if I manage to prove that this geodesic coalesce and that they don't intersect the cube, plus if I manage to prove that any path from here to here does not do something like that, then I trapped all the geodesic and I have what I want. So I have many things to check. I have to check that if the geodesic here don't intersect the cube. I have to check that the points in the cube here, they cannot escape my trap by going backward. And I have to check that the geodesic indeed coalesce. And to be sure that the geodesic cannot escape and that this cannot intersect the cube, it actually is the same arguments, and that's where we use our assumption on the side. Because on our assumption on the side really enable us to control the fact that the geodesic that goes, for instance, in that direction, we can control the fact that it goes in some angle compared to the direction that it has to go. We can control the fact that the geodesic go for a long time in a wrong angle. Because here, you see here, you want to go in like this angle. And so here, if you want to escape, you have to go really in a wrong angle. And the more size you have, the more you can control the geometry and control the fact that the geodesic like do something that is not optimal for a long time. And just to give a more intuition on that, is just like if you have 2 sides like that, you know that if you go like, and you want to go like here, you know that going like here, if it's not the same side, you know that it will cost you more. And so you cannot go like more than over the square root 10 in this direction. And the more side you get, the more you can make this square root 10 go down. So if you haven't understood, it's okay. Just remember that the more sides you have, the more you can control the geometry. And of course, if you have like differentiabilities, like having an infinite number of sides, you can really control the fact that some geodesic go from a polynomial time in a wrong angle compared to where it has to be. Okay, so now we are sure that it's a trap, but it's a trap only if these 2 geodesic coalesce. And so how can we make sure that they coalesce? So we already know that like for instance, the one below has a lot of attractive intervals. And so to be sure that they coalesce, we have to be sure that the geodesic above goes. So we have, let me make a picture. So you have the geodesic above. So it has a lot of good intervals. So there are sparse, but there are a lot of them. And so if we make sure that the geodesic above come close a lot of time, if we make sure that the geodesic above come close to the geodesic below a lot of time, then it's enough to have only one time where it got really close to an attractive interval to coalesce. For instance, here I came very close from an attractive interval, and then I coalesce. And I need just one more in the other side. And for instance, here I coalesce. And if I know that I coalesce like 2 times, I know that in between, since you only have one unique geodesic, you know that it will follow the path. So to make sure that the 2, the below and the above coalesce, I have to make sure that they stay close most of the time. That I can make them close most of the time. And I have to make them close on more intervals that they have I have to make sure that the number of intervals where they are not close to each other is smaller than the number of non-attractive intervals, so that I'm sure that there is at least one interval where they are both close and it's in attractive interval. Because I really want that on almost all intervals they are close. And to be sure that they are close to each other, in fact, it's just a Markov inequality. Because like this geodesic is just a translate of this one, of size, so it's some size here, h. So it's just a translate of this one. So if you look at the so let's say it's gamma minus and gamma plus. If I look at gamma minus, let's write it like, so it's kind of a weird notation, but gamma minus x is like the height at the first time you hit the x here. X is on the axis. Maybe yes. So you put the you have an x and you look at the height at the first time it hit this one. So maybe x is not a good notation. Let's call it let's call it q, because it's more like an integer. It's you look at this axis at position x equal q, and you look at the height of the first point of gamma minus. And so if here you have that gamma plus is a translate of gamma minus, then this plus h is equal to the expectation of gamma plus q. Just because, again, using translation invariance. And so so here you are just using translation invariance. Just you look at the same geodesic. If you started h above, then the expected time will be h above. That's just what it says. And then you have that the expectation of gamma plus q minus gamma minus q is equal h. And in fact, again, using the same condition that they cannot go below, they always stay ordered. And this is really crucially where we use the dimension 2. We can really prove that they always stay ordered. They are always one above the other. Gamma plus will be always with really high probability, like exponentially high probability, will be always above gamma minus. So this, it's actually, you can put absolute value and it only changes by a constant. And so now if you can, now that you have that, you can just use Markov inequality to say that with really high probability, this thing is going to be smaller than t times h, where t is something large. And so then the remaining is just really using Markov inequality to be sure that on almost all intervals you are really close to the geodesic. And then it's just computations, and you have to make everything quantitative to be sure that gamma plus coalesce with gamma minus. So I will stop here. So thanks for your attention.
Further questions for Barbara? Anyone on Zoom have further questions? Maybe could you say just a little more about the condition on the number of sides, how this helps you, how it helps you trap? Because it feels like if you have a polygon, just having a large finite number of sides still will let you kind of wander linearly, and it's hard to see why having, you know, a slope at most something would be helpful. Is it easy to see?
Yeah. Let me do a picture. So let's say you look at a geodesic from here to here. So the first step is to say that you cannot reach this line at a distance greater than this distance here, that will be smaller than square root n. And
Okay.
this is just because you have the, you know that at the linear scale, it's going to, the difference between doing that and doing that is linear. And since you have like Talagon concentration inequality, you can only, you have only fluctuation of square root n. So if you go square root n in this direction, it can be still compensated by the fluctuation,
Right.
but not more. And then you go on like that. You know that if you go do, you are here, then you cannot be more than n to the 1/4 here. And then you go on and go on, because for the, just for the same reason, like the path from here to here, it's a path of length at most square root n. And so this is a wrong direction for it. And again, the fluctuation at most n to the 1/4, and so it cannot go longer, otherwise it's not compensated. And you can do that again and again.
Okay, I see. Yeah, thank you. Any other questions? If not, let's thank Barbara again.